Hey guys, today I'm going to be talking about capacitors and capacitance. So first off, what is capacitor? Well, a capacitor is a device that's designed to store electric energy, and basically it looks sort of like this. So there's like two plates in proximity with each other, and they have the same charges but with opposite signs. So for instance, if this is plus Q, this charge would be minus Q. And when they're charged, there's a voltage across the plates. And yeah, as I said earlier, they bear equal and opposite charges. So in the field, the electric field would look something like this for the plate. And so, what is capacitance? Well, capacitance is a measure of sort of how effective a capacitor is, and it's a measure of how much charge it has over its like potential difference. The formula for capacitance is the charge, well, over the potential difference or voltage. And the units are coulombs per volts, which is also the same thing as farads, which is an F. And a farad is considered to be realistically like a very, very high capacitance. You're actually a lot more likely to see millifarads, microfarads, nanofarads, and even picofarads, which are a thousandth of a farad, a millionth of a farad, a billionth of a farad, and even a trillionth of a farad, respectively. So yeah, farads are the units for capacitance, and they're equivalent to coulombs per volt. So how a capacitor works is, so first off we have the circuit. So that's the battery, and the capacitor looks something like this. And in this case, current would be flowing counterclockwise. So basically, the current goes through it, and it goes from high potential to low potential. And sometimes capacitors have this thing between them. It's an insulating material, and it's called a dielectric. And this helps them better store the electric potential energy. So then how would we find like how much energy a capacitor is storing? Well, the formula for that is the stored energy in a capacitor is equal to 1/2 times the capacitance, which I mentioned earlier, times the voltage squared, which can also be written as the charge squared over twice the capacitance. So this is the formula for the energy stored in a capacitance. And as I said earlier, this is the general formula for capacitance. And there's more specific formulas depending on like the shape of the capacitor and also the dielectric. So the first type of capacitor we'll be looking at is a parallel plate capacitor, and it's pretty self-explanatory. So there's basically two plates. They have the same like area, their distance d from each other, and as I said earlier, for all capacitors, they have charges that are equal in magnitude but opposite in sign. And in this case, the field would be flowing this way, and they might have a dielectric between them. So the formula for specifically a parallel plate capacitor is it's equal to kappa times epsilon naught times the area over d. So what do each of these quantities mean? Well, first off, kappa is known as the dielectric constant. And as I mentioned earlier, sometimes for capacitors, there's an insulating material between the plates. It's known as a dielectric. It helps to better store energy inside the capacitors, and this constant accounts for that. And if there's nothing between the capacitors, so basically just thin air, the constant is roughly equal to 1, so you can pretty much just neglect it. And the next variable or constant rather is epsilon naught. It's known as the permittivity of free space, and it's equal to 8.85 times 10 to the negative 12. And I forgot the units, but I could derive that if I wanted to. And next up is the area, which is denoted by A. It's in meters squared, and it's the area of just one of the plates, so not both of them. And the final quantity, which I mentioned earlier, is d, which is just the distance between plates. and it's in meters. And we can actually derive this formula using the original formula quite easily, and I'm going to actually do that right now. So let me just redraw our capacitor. So let's say these are the two parallel plates. This one's positively charged, this one is negatively charged, and we have the field should be flowing this way. And this, and then we'll just say this has a charge of plus Q, this has a charge of minus Q. And there's basically in physics, there's this quantity known as the surface charge density. It's denoted by lowercase sigma. It's the amount of charge over a certain area. And this will come in handy later on in this derivation. So our first step is to try to find like an expression for the electric field. And we can do that using Gauss's law of electricity, which basically states that the electric flux over a closed surface, so this is the formula for that, is equal to the charge enclosed in that surface over the constant epsilon naught, the permittivity of free space. I mentioned it earlier up here. So yeah, it's equal to that. And because this is a relatively simple surface, we can actually just completely simplify this integral to just equal EA. Since the field vectors are perpendicular to the surface, we can completely just ignore the dot product. And then we can once again set this as equal to Q over epsilon naught. And remember earlier I said that the surface charge density is Q over A. So it follows that Q is sigma times A. So then we can rewrite this now as sigma times A over epsilon naught. And we can see we can just cancel out the A's. And so we get that the magnitude of the electric field is equal to the surface charge density over epsilon naught. And our next step would be to find the voltage, which is the whole point of finding the electric field, because the equation for voltage is sort of in terms of the electric field. And the equation for voltage is this. So it's an integral. And first off, what are the bounds? Well, as I mentioned earlier, the distance between the plates is known as d. So what we can do is we can call this left plate where the field starts as 0, and we can call this d. So then we can set up our bounds as from 0 to d. And then we already calculated the value for E, which is sigma over epsilon naught. So we can then rewrite this as sigma over epsilon naught times dr from 0 to d. And if we integrate this, we can find that it's pretty much just negative this times d. So then we get negative sigma times d over epsilon naught. And yeah, we're almost done. So as I mentioned earlier, the general formula for capacitance is charge over voltage. And we just found out the voltage. So now what we can do is we can just pretty much divide. And since capacitance has to be positive, we need to just ignore this negative sign. So we get this. And then as I said earlier, Q is just equal to sigma times A. So we can replace Q with sigma times A. We can see there's a neat cancellation with the sigmas. So we get A over D over epsilon naught. And if we simplify this, we can see we get epsilon naught times A over D. And if you recall, the formula I said earlier for parallel plate capacitors is kappa times epsilon times A over D. So if we take into account the dielectric between the plates, then yes, we would have to multiply this by the dielectric constant. And we would see that we would just get this formula. So yeah. The next type of capacitor, well, there's several types. I'm just going to be covering 2 for this video, is a cylindrical capacitor. So consider a capacitor where, so let's say we have this circle here, and this is going to be like the inner cylinder, and it's a conductor. And let's say it is, the outside of it is positively charged. Then there's a shell here, and this is negatively charged. So then we would know that the field would have to be going radially outwards, like so. And let's say that this inner cylinder, so this is the front view of the cylinder, has radius A, and it's kind of hard to see, but yeah, radius A. And this outer one has radius B. And let's say that the cylinder has length L. So we're going to derive a formula for capacitance now, specifically for a cylindrical capacitor. So first step is to make a Gaussian surface. And in my video on Maxwell's equations, I covered that, so you can refer to that. So basically, I'm going to draw an sort of imaginary cylinder between the two. And I'm going to give this radius R. And so, once again, we're going to use Gauss's law of electricity, which states that the electric flux over a closed surface is just equal to the charge enclosed over epsilon naught. In this case, our closed surface is going to be this imaginary surface inside the imaginary cylinder with radius R. And once again, we can sort of simplify this integral to just equal E times A. For more complex surfaces, yes, you will have to actually like compute the integral, but this is just a cylinder, so it's pretty straightforward. And then, so we need to find which part of the cylinder actually experiences flux or has electric fields going through it. So if we look at this picture here, which I'm circling right now, so we would see the fields would go sort of radially outwards like this. But they wouldn't really be going out through the faces. Or if they were, they'd be canceled out by other fields in opposite directions. So we wouldn't pay attention to these faces. So when we're using the area part, this part, we're only going to take the area of the cylinder, the lateral surface area, I should say. I believe that's what it's called. So this part that wraps around. We're going to completely ignore the faces. And we said that the length is L, so the lateral surface area would be equal to, if I recall correctly, 2 pi RL. So then we're just gonna find E. So it's Q over 2 pi. So we're plugging in that for A now. 2 pi epsilon naught RL, yeah. Okay, and then we would just do what we did in the previous problem. So we would get that equation for voltage we had earlier. And this time, we said that the radii were A and B, and since the field goes radially outwards, we're going to be integrating from A to B. Since, keep in mind, the charges of conductors are always on the outside. So for A, it's going to be on the outside of the surface. That's why it's starting at A. For B, it's going to be at the outside of the surface. So that's why we're ending at B. And then it's just this dot product for the integrand. And then we already found E, which was this. And we can see we can take out most of it, except for R, which we will have to leave in the integral, but the rest of it is pretty much constant. So we can then rewrite this as negative Q over 2 pi epsilon naught L, integrated again from A to B, and inside is dr over R. And then this would just give us negative Q 2 pi epsilon naught times L times the natural log of B over A. Because remember that the natural log of B minus the natural log of A is equal to natural log of B over A. That's just one of the properties. And then since we want capacitance to be positive again, we're just going to get rid of this, ignore this negative sign. And yeah, so then, as I said earlier, the general formula is Q over the voltage, the charge over the voltage. So in this case, we found that this expression here is the voltage. So we just divide, and we can already see that we can cancel out the charges. And when we divide, we get that the capacitance for a cylindrical capacitor is 2 pi epsilon naught L over the natural log of B over A. So yeah, this is the derivation. So now that that's all good, how exactly do capacitors work in circuits? Well, so let's draw a circuit first of all. So it looks like this. And let's say we have a capacitor here, and the current in this case would be going in this direction. And let's say this has a capacitance of, let's just say 2 farads, and this has capacitance of 4 farads. So first of all, let's say we need to find what the equivalent capacitance is. Well, first of all, what is the equivalent capacitance? Well, equivalent capacitance is a term for like, what would the capacitance be if you were to combine these two capacitors into one, which had the same effect as both of them combined. So then, well, first off, these capacitors are in what we would call series, and what that basically means is that the current to go in a full path around the circuit, it has to go through both of the capacitors. So if it goes through C1, we're going to call it C1, it has to go through C2. And because they're on the same path, they're in series. And later I'll get to what is known as parallel, but for now we'll focus on series. The formula for adding up capacitances in series is basically 1 over, or the reciprocal of the sum of the capacitances in series is equal to the sum of the reciprocals of the individual capacitances. So that's quite a mouthful, but I'm going to show how it works. So in this case, since both capacitances are in series, we can just say 1 over the equivalent capacitance, which is what we want to find, is equal to. So we see this one's 2 farads, this one's 4 farads, so it's actually pretty simple. So we just add them up, and if we do this, we get 3/4. But keep in mind, this is the reciprocal, so we have to find the reciprocal again. So we get that the equivalent capacitance is 4/3, which is about 1.33 farads. Yep. So yeah, that wasn't too bad. And now we're going to be looking at what if capacitors are in parallel. So I'm going to redraw another circuit. And this time we're going to have the same capacitances. So this is C1, it has capacitance of 2 farads. And the current will be going counterclockwise again. And this is C2, and it has capacitance of 4 farads. And this time, we can see that the current has to sort of choose which path to go in, or it can't go, like, they're not in the same path, basically. So that's what is called in parallel. So these two are in parallel with each other. And keep in mind, that doesn't necessarily mean they're in parallel. Like C2 could be over here. It just means that they're not on the same path. So it's sort of, they're separated by a junction here, basically. So yeah, so how would we add capacitances in parallel? Well, it's actually a bit easier than adding them in series. To add capacitances in parallel, you actually pretty much just add them up. That's all. Like, yeah, it's super easy. So then, since both of these are in parallel, the equivalent capacitance is just 2 farads plus 4 farads, which is 6 farads. So yeah, pretty simple. Not too bad. Now, what if we had them in series and in parallel? Well, that's actually nothing new. It's not too bad. So I'm going to draw this, and I'll draw another one here. So we can see that these two are in series, and this one with this one and this one are in parallel because they're separated by a junction. Well, first off, I'm not actually going to solve anything. I'm just going to explain it. I think it should be fairly easy to get. But so first off, you would combine the two in series using that formula I mentioned earlier, which I will rewrite. Yeah, so you'd combine them into one. So now this, we can call it, I don't know, C prime. This would be the combined effect of those two in series. And then we would have that the other original capacitor, which, so if we call this C1, C2, C3, this one would still be C3. And now we can just see all we have to do is combine these two in parallel using this formula. So in this case, the equivalent capacitance would just be C prime plus C3. And boom, we would have the equivalent capacitance. So yeah, it's not too bad. So yeah, these are basically the basics of capacitance and a few of the different types of capacitors, how capacitors work, their purposes. And yeah, thank you for watching. I hope this video helped, and see you later.